A review of DeepSeek models' key innovative techniques. Chenjen Wang, University of Texas, at Dallas. Chenjen.Wang at Dallas.edu. Murat Kantarsioglu, Virginia Tech. Murat at VT.edu. Abstract: DeepSeek v3 and DeepSeek R1 are leading open-source large language models (LLMs) for general-purpose tasks and reasoning, achieving performance comparable to state-of-the-art closed-source models from companies like OpenAI and Anthropic, while requiring only a fraction of their training costs. Understanding the key innovative techniques behind DeepSeek's success is crucial for advancing LLM research. In this paper, we review the core techniques driving the remarkable effectiveness and efficiency of these models, including refinements to the transformer architecture, innovations such as multi-head latent attention and mixture of experts, multi-token prediction, the co-design of algorithms, frameworks, and hardware, the group relative policy optimization algorithm, post-training with pure reinforcement learning, and iterative training alternating between supervised fine-tuning and reinforcement learning. Additionally, we identify several open questions and highlight potential research opportunities in this rapidly advancing field. Keywords: DeepSeek, multi-head latent attention, mixture of experts, group relative policy optimization GRPO. 1. Introduction. The emergence of ChatGPT in late 2022 OP25A ushered in a new era of large language model (LLM) research. LLMs have since advanced rapidly, with models like GPT-OP25B and Claude Ant25 demonstrating exceptional performance. While open-source LLMs such as LLaMAGDJ Plus 24 have achieved competitive results in certain metrics, their overall performance still lags behind proprietary models. In January 2025, DeepSeek rattled markets and made headlines Ru25 with DeepSeek v3 LFX plus 24 and newly launched DeepSeek R1 models GYZ plus 25. These models achieve performance comparable to that of state-of-the-art GPT models, while requiring only a fraction of training resources. Understanding the techniques underlying the remarkable effectiveness and efficiency of these models is crucial for advancing LLM research. In this paper, we review the key techniques behind DeepSeek models' success. These include the refinement to the transformer architecture, specifically multi-head latent attention MLA and mixture of experts MOE, multi-token prediction, the co-design of algorithms, frameworks, and hardware, the group relative policy optimization GRPO reinforcement learning algorithm, and post-training techniques, such as pure reinforcement learning and multi-stage iterative training that alternates between supervised fine-tuning SFT and reinforcement learning. Additionally, we identify several issues that are not addressed in DeepSeek's technical report or ablation studies, highlighting potential research opportunities. In the following, we first provide a concise yet in-depth review of the above-mentioned innovative techniques in Section 2, followed by a discussion of the open problems and potential research directions in Section 3, and conclude the paper in Section 4. To the innovative techniques in this section, we examine the key innovative techniques that drive the success of the DeepSeek models. While these techniques are integrated into DeepSeek v3 and DeepSeek R1, some may have won RZIV:2503.11486V1CS.LG14 Mar 2025. Been introduced in earlier DeepSeek models. 2.1 Multi-head latent attention KV cache is a technique used in the multi-head attention MHA block of a transformer to accelerate inference by storing intermediate keys and values, eliminating the need for repeated calculations. However, the KV cache can become a bottleneck for long-context LLMs due to their high memory consumption. One approach to reducing the KV cache is to employ fewer attention heads, as seen in multi-query attention MQA SHA-19 and group query attention GQA ALCH plus 23. Despite this, their performance does not match that of MHA. Later, an innovative attention mechanism called multi-head latent attention MLA is proposed for DeepSeek v2 LFW plus 24, which requires far less KV cache while achieving better performance. 2.1.1 Standard multi-head attention. In the standard MHA VSB plus 17, the queries, T's and values are obtained through the projection matrices WQ, WK, WVRDH and H times D, transforming HTRD, the input of TTH token, to queries. T's and values QT equals WQHT, KT equals WKHT, BT equals WVHT, QT, KT, BTRDH and H, respectively, where D is the dimension of the input embedding, and H is the number of heads and DH is the dimension per head. The dimension DH times NH indicates how the QT, KT, BT are sliced into NH heads with dimension DH per head for the multi-head attention mechanism LFW plus 24, EC. 4, 8. QT1 QT2, QTNH equals QT1. KT1 KT2, KTNH equals KT2. VT1 VT2, VTNH equals VT3. OTI equals TXJ equals 1 soft XJQTTIKJI square root DHVJI 4. UT equals WOOT1, OT2, OTNH 5. Where QTI, KTI, VTI, RDH represent the query, key, and value of the IDH head, respectively, and WORD times DHNH is the output projection matrix. During inference, each token requires KV cache of size 2 and HDHL, where L is the number of layers. Grouped query attention GQA multi-head attention MHA multi-query attention MQA multi-head latent attention MLA. Keys queries values projection compressed latent KV cached during inference figure 1, a simplified illustration of multi-head attention MHA, grouped query attention GQA, multi-query attention MQA, and multi-head latent attention MLA. Adapted from LFW plus 24, figure 3. 2.1.2 Low-rank key-value joint compression. The core idea of MLA is to decompose the projection matrix into two lower-rank matrices, W equals WUWDKV, where WDKV RDC times D is the down projection matrix for both keys and values, WURDH and H times DC is the up projection matrix, and DCDH and H. The down projection matrix compresses both keys and values into one latent vector CKVT equals WDKVHT, CKVT RDC LFW plus 24, EC. 9. Since DCDH and H for each token, saving CKVT of size DCL instead of both KT and VT of size 2DH and HL greatly reduces the KV cache. 2. The keys and values are computed from the latent vector CKVT as follows: LFW plus 24, EC. 10, 11. KCT equals WUKCKVT, 6. VCT equals WUVCKVT, 7. Where WUK, WUVRDH and H times DC denote the up projection matrices for keys and values, respectively. Importantly, WUK will be absorbed into WQ and WUV absorbed into WO during inference, so we do not need compute KCT, BCT explicitly. The architecture of MLA is illustrated in Figure 1. Moreover, low-rank compression of queries is applied to reduce the activation memory during training LFW plus 24, EC. 12-13. CQT equals WDQHT, 8. QCT equals WUQCQT, 9. Where CQTRDC represents the compressed latent vectors for queries, with DCDH and H, and WDQRDC times D, WUQRDH and H times DC denote the down projection and up projection matrices, respectively. 2.1.3 Decoupled rotary position embedding. DeepSeek v2 utilizes the rotary position embedding rho PESAL plus 24. QTIKJ equals HTIWQ. T rho P theta J minus IWKHJ10 equals HTIWQ. T rho p theta j minus IWUKW DKVHJ11, where rho p theta ji denotes the operation that applies the rho p matrix. Theta is predefined parameters, and I, j are the ITH and JTH positions. As a result, WUK will not be absorbed into WQ, leading to significant computational cost during inference. To address this issue, DeepSeek v2 proposes to decouple rho p into a separate set of queries and keys. Multi-head queries QRTIRDRH and a key KRTRDRH shared by all heads, where DRH represents the per-head dimension of the decoupled queries and keys. This decoupling strategy essentially computes two separate sets of attention weights, which are then added together. The full MLA computation is as follows: LFW plus 24, EC 1419, QRT1, QRT2, QRTNH equals QRT equals rho PW QRCQT 12, KRT equals rho PW KRHT 13, QTI equals QCTI QRTI 14. KTI equals KCTI, KRT 15. OTI equals TXJ equals 1 SOFX JQTTIKJIQDH plus DRHVCJI 16. UT equals WOOT1, OT2, OTNH 17. Where WQRRDRHNH times DC and WKRRDRH times D denote matrices used to generate the decoupled queries and key, respectively. Rho p refers to the operation that applies the rho p matrix, with the subscripts omitted, and represents the concatenation operation. During inference, the decoupled key KRT with dimension DRH is also cached. As a result, each token requires cache of size DC plus DRHL in total. For DeepSeek v2, where DC equals 4DH and DRH equals DH2, the KV cache per token is 92DHL. It has been reported that MLA outperforms MHA LFW plus 24, Table 9, which is surprising considering that MLA uses low-rank matrices, inherently containing less information than the original projection matrices for keys and values. Therefore, this performance gain is likely due to the introduction of the decoupled rho p, which differs from the original rho p. However, no ablation study for the decoupled rho p has been reported, making it a worthwhile direction for further investigation. 1 2 letter 1 D4 4 1 letter 1 D4 4 1 router input hidden output hidden. Router input hidden output hidden 1 2 3 4 2 letter 1 D4 4 1 letter 1 D4 4 1 1 2 letter 1 D4 4 1 letter 1 D4 4 1. Router input hidden output hidden 1 2 3 4 2 letter 1 D4 4 1 letter 1 D4 4 1 1 2 letter 1 D4 4 1 letter 1 D4 4 1 shared expert routed expert letter 1 D4 3 letter 1 D4 3 equals 2 letter 1 D4 3 letter 1 D4 3 equals 4 letter 1 D4 3 letter 1 D4 3 equals 3 a conventional top 2 routing B plus fine-grained expert segmentation C plus shared expert isolation DeepSeek MOE 2.2 Mixture of Experts MOE is an architecture designed to reduce computational cost while scaling up model parameters. In an MOE model, the feed-forward network FFN layers in a transformer are typically replaced with MOE layers at specified intervals. Each MOE layer consists of multiple experts, all structurally identical to a standard FFN. Tokens are routed to one or two experts FCS22, LLX plus 20. The DeepSeek MOE architecture DDZ plus 24 introduces two key innovations: fine-grained expert segmentation and shared expert isolation. These innovations are built upon the conventional MOE. 2.2.1 Fine-grained expert segmentation on top of the conventional MOE architecture shown in Figure 2. HFFN is segmented into M smaller experts by dividing the FFN hidden dimension evenly. As a result, if the total number of experts is N and the number of activated experts for each token is K in a conventional MOE, then the total number of experts is increased to Mn and the number of activated experts is increased to Mk for a fine-grained MoE architecture, as illustrated in Figure 2b. This fine-grained segmentation strategy greatly improves the combinatorial flexibility of the activated experts. 2.2.2 Shared Expert Isolation. Shared experts are dedicated to capture the common knowledge across diverse contexts, reducing parameter redundancy among different experts. Specifically, KS experts are reserved as shared experts, and each token will be always assigned to these shared experts in addition to their respective routed experts. To maintain a constant computational cost, the total number of routed experts NR is reduced to Mn-Ks and the number of routed experts for each token is Mk-Ks. With the novel strategy of fine-grained expert segmentation and shared expert isolation, and MoE layer in the DeepSeek MoE architecture is defined as follows: DDZ plus 24, EC 911. HLT equals KSXI equals 1 FFNI. GIT equals SIT, SIT top SJTKS plus 1 less or equal to J less or equal to MN, MK minus KS, 0, otherwise, 19. SIT equals softmax IULTTELI, 20. Where FFNI refers to the IDH expert FFN, ULTRD is the hidden state of the TTH token after the LTH attention module, and HLTRD is the output hidden state of the TTH token after the LTH MoE layer. GIT represents the gate value for the IDH expert, SIT is the token to expert affinity, top. K gives the set of top K affinity scores calculated for the TTH token across all N experts, and ELI represents the cent rate of the IDH expert in the LTH layer. 2.2.3 Load balancing. The automatically learned routing strategy may face the issue of load imbalance, where either a few experts are always selected while others are not sufficiently trained, or the activated experts are distributed across multiple devices, leading to significant inter-device communication cost. These issues are addressed by an auxiliary loss for load balancing FCS 22. The expert level balance loss is formulated as follows: DDZ plus 24, EC 1214. LXBAL equals alpha NXI equals 1 FIPI 21. FI equals NKTTXT equals 1 token T selects expert I 22. PI equals 1 TTXT equals 1 SIT 23. Where alpha is a hyperparameter, n equals mn minus ks and k equals mk minus ks for simplicity, and 1 represents the indicator function. When the load is uniformly distributed among the experts, LXBAL is minimized, fi equals 1, pi equals kn, and we have pni equals 1 fipi equals n1 kn equals k. Let Fi and Pi be the normalized version of Fi and Pi, respectively. Fi equals Fin, Pi equals Pik, such that both form probability distributions. The limitation of this expert level loss formulation is that when Pi is uniformly distributed, i.e., Ti equals 1n for all I, then for any distribution of Fi, we have Pni equals 1 Fipi equals Pni equals 1 Fik equals k. Under these circumstances, the auxiliary loss fails to push toward balanced experts utilization. If a uniform distribution of Pi inherently produce a uniform distribution of Fi in practice, then incorporating Fi in the loss function appears redundant. Given the widespread adoption of this formulation FCS 22, LFX plus 24, JZI 24, it is worthwhile to investigate its theoretical justification and explore potential improvements. Besides expert-level load balancing, device-level and communication load balancing DDZ plus 24, LFW plus 24 are proposed to ensure balanced computation and communication across different devices. The formulations of these loss functions follow a similar pattern. Since the auxiliary loss may degrade model performance, an auxiliary loss-free load balancing strategy is proposed to strike a better trade-off between load balance and model performance. WGZ plus 24. Specifically, a bias term BI for each expert I is added to the affinity score SIT to determine the top gay selection LFX plus 24, EC. 16. GIT equals SIT, SIT plus BI top SJT plus BJ1 less or equal to J less or equal to NR, KR, 0, otherwise, 24. Where NR represents the number of routed experts and KR is the number of activated routed experts. During training, the bias term BI will be decreased by gamma if the expert is overloaded and increased by gamma if the expert is underloaded, where gamma is a hyperparameter. Note that the bias term is used solely for top K selection and the gating value is still using the original affinity score SIT, as shown in EC. 24. In this equation, SIT plus BI serves as the input to the top function, while SIT is the value of GIT if SIT is among the top gay. In DeepSeek v3, a complementary sequence-wise auxiliary loss is also employed to avoid extreme imbalance within any single sequence LFX plus 24. 2.3 Multi-token prediction. DeepSeek v3 employs multi-token prediction MTP GIR plus 24 to improve training performance. For each token, instead of predicting next token only, MTP predicts the additional tokens in a causal chain. Main model next token prediction. Embedding layer output head transformer block embedding layer letter 1 D461 letter 1 D4612 letter 1 D461 letter 1 D4613 letter 1 D461 letter 1 D4614 letter 1 D461 letter 1 D4611 letter 1 D461 letter 1 D4613 letter 1 D461 letter 1 D4614 letter 1 D461 letter 1 D4615 letter 1 D461 letter 1 D461 shared concatenation output head transformer block embedding layer linear projection MTP module 2 next 3 token prediction. Concatenation shared letter 1 D461 letter 1 D4613 letter as shown in figure 3. At each depth K of the DMTP modules, there are a shared embedding layer and a shared output head, an independent transformer block, and an independent linear projection layer. The input to the linear projection layer is an concatenation of the embedding at the current depth and the output embedding from the previous depth. The MTP training objective, LMTP, is the average of the cross-entropy loss LKMTP at each depth K1, 2, DLFX plus 24, EC. 24-25. LKMTP equals cross-entropy PK2 plus K colon T plus 1, T2 plus K colon T plus 1 equals minus 1 TT plus 1 XI equals 2 plus K log PKITI, 25. LMTP equals lambda DDXK equals 1 LKMTP, 26. Where T represents the length of the input sequence, Ti is the ground truth token at the ith position, and PKITI denotes the prediction probability of Ti at depth K. The advantage of MPP lies in its higher sample efficiency during training GIR plus 24, leading to improved performance. However, the causal chain formed by the MTP modules introduces additional training time overhead beyond conventional next token prediction, a factor not addressed in the ablation study for MTP in DeepSeek v3 LFX plus 24, Sec. 4.5.1. 2.4 Co-design of algorithms, frameworks and hardware. Through the co-design of algorithms, frameworks and hardware, with meticulous engineering optimizations, DeepSeek v3 significantly enhances the training efficiency and completes the pre-training of the model on 14.8 trillion tokens with 2.788 million H800 GPU hours LFX plus 24. Device 0012 Device 001234. The microbatches in the reverse direction are symmetric to those in the forward direction. Adapted from LFX plus 24, figure 5. 2.4.1 Dual pipe to reduce the communication overhead introduced by cross-node expert parallelism. An innovative pipeline parallelism algorithm called dual pipe LFX plus 24 is proposed to overlap the computation and communication within a pair of individual forward and backward chunks. The algorithm divides each chunk into 4 components, with the backward computation chunk further divided into 2 parts for input and weights, respectively QWHL23, to reduce pipeline bubbles. A specific ratio of GPU SMs are dedicated to communication, ensuring that communication remains fully hidden during execution, effectively achieving near-zero all-to-all communication overhead. The dual pipe algorithm employs a bidirectional pipeline scheduling, feeding data from both ends of the pipeline, as illustrated in Figure 4. Dual pipe requires keeping 2 copies of the model's parameters, leading to additional memory consumption. It turns out the bidirectional part is unnecessary and can be removed with a cut-in-half procedure, as outlined in QWHL 25. 2.4.2 FP8 Mixed Precision Training. A mixed precision framework for training DeepSeek v3 is introduced for efficient training without accuracy degradation. In order to accelerate training, the majority of core computation kernels general matrix multiplication GEM are implemented in FP8 Precision DLBZ22, PWW plus 23, FCBS 24. Despite the efficiency advantage of FP8 format, DeepSeek v3 maintains the original precision for certain operators due to their sensitivity to low-precision computations, to balance training efficiency and numerical stability. These operators include the embedding module, the output head, MOE gating modules, normalization operators, and attention operators. This framework utilizes a fine-grained quantization strategy to extend the dynamic range of the FP8 format, tile-wise grouping with 1 times NC elements or block-wise grouping with NC times NC elements, where NC is the channel size, with NC equals 128 in DeepSeek v3 model. The accuracy of low-precision GEM operations largely depends on high-precision accumulation. DeepSeek v3 employs a strategy of promotion to CUDA cores for higher precision, periodically copying intermediate results to FP32 registers on CUDA cores at an interval NC for full precision FP32 accumulation. Letter 1D45E, Letter 1D45E, Letter 1D45C, Letter 1D45C. Letter 1D45C, Letter 1. Policy model reference model reward model PPO GRPO trained models frozen models reference model letter 1D43 letter 1D43 letter 1D43 letter 1D43 letter 1D43 GRPO estimates the baseline from group scores without a value model. Adapted from SWZ plus 24, Figure 4. 2.5 Group Relative Policy Optimization GRPO SWZ plus 24 is an efficient and effective variant of proximal policy optimization PPO SWD plus 17. GRPO eliminates the value function approximation in PPO by directly estimating the advantage, significantly reducing memory usage. In the context of LLM, where typically only the last token is assigned a reward, the training of a value function in PPO is challenging. The simplified GRPO can achieve comparable performance while being more efficient. More specifically, the PPO maximizes the following objective SWZ plus 24, EC. 1. JPPO theta equals EQPQ, O pi theta old OQ100XT equals 1 min. Pi theta OTQ, OT. Pi theta old OTQ, OT. ET, clip pi theta OTQ, OT. Pi theta old OTQ, OT. 1 minus epsilon, 1 plus epsilon. ET hash, where Q, O represent questions and outputs. Pi theta and pi theta old are the current and old policy models, respectively, and epsilon is a hyperparameter related to clipping, and a t represents the advantage, which is estimated using rewards and a learned value function. Instead of training a value function, GRPO directly estimates the advantage by sampling a group of outputs O1, O2, OG from the old policy pi theta old, yielding G rewards R equals R1, R2, RG, scored by a reward model. There are two ways to estimate the advantage: outcome supervision and process supervision. Output supervision provides a reward at the end of each output OI and set the advantages letter to C6 IT of all tokens to the same normalized reward, i.e. letter to C6 IT equals I equals RI minus mean R. STDR SWZ plus 24 sec 4.1.2. Process supervision provides a reward for each intermediate steps, and then calculate the advantage for each token by summing the normalized rewards obtained from the subsequent steps. GRPO maximizes the following objective: SWZ plus 24, EC 3. JGRPO theta equals EQPQ, OIGI equals 1 pi theta old OQ1 GGXI equals 1 1 OI OIXT equals 1 min. Pi theta OITQ, OIT. Pi theta old OITQ, OIT. Letter to C6 IT, clip pi theta OITQ, OIT. Pi theta old OITQ, OIT. 1 minus epsilon, 1 plus epsilon. Letter to C6 IT hash minus beta DKL pi theta pi ref. 28. Where pi ref is the reference policy model, typically the initial base model or the SFT model. The GRPO algorithm is illustrated in Figure 5. 2.6 Post-training. Reinforcement learning on the base model. 2.6.1 Pure reinforcement learning. DeepSeek R10 GYZ plus 25 is trained on the base model DeepSeek v3 base with pure reinforcement learning RL without any supervised fine-tuning SFT data. The performance of DeepSeek R10 continuously improves throughout the RL training process. The reasoning behaviors, including reflection and the exploration of alternative approaches, naturally arise during the training, demonstrating the effectiveness of pure RL and the model's capability to learn and generalize solely through RL. DeepSeek R10 utilizes the GRPO algorithm, as outlined in Section 2.5. The reward function includes two types of rewards: accuracy rewards, which assess the correctness of the model's response, and format rewards, which enforces the model to enclose its thinking process within the tags think and /think. A training template is designed to guide the model in following the specified format, first generating a reasoning process before presenting the final answer. Although DeepSeek R10 achieves remarkable performance through pure RL, it encounters challenges such as poor readability and language mixing. To mitigate these issues and further enhance the model, DeepSeek R1 GYZ plus 25 is introduced, which employs an iterative training approach that alternates between SFT and RL. 2.6.2 Reinforcement learning with cold start. DeepSeek R1 employs a training pipeline consisting of 4 stages GYZ plus 25. Cold start. To mitigate the instability of the early cold start phase of RL training, thousands of long chain of thought TWWS plus 22 examples are collected to fine-tune the DeepSeek v3 base model, which then serves as the foundation for subsequent reinforcement learning. Reasoning-oriented RL. After fine-tuning DeepSeek v3 base on the cold start data, the model undergoes the same RL training process as employed in DeepSeek R10. To address language mixing, an additional language consistency reward is introduced, measured as the proportion of target words in the COT. Rejection sampling and SFT. The goal of this phase is to improve the model's performance in writing, role-playing, and other general-purpose tasks. Once reasoning-oriented RL converges, 600K reasoning-related training samples are collected via rejection sampling from the checkpoint, retaining only the correct responses. Additionally, approximately 200K non-reasoning training samples are collected, either from parts of the SFT dataset of DeepSeek v3 or generated by DeepSeek v3. RL alignment. This phase aims to better align the model with human preferences by improving its helpfulness and harmlessness while also refining its reasoning capabilities. Helpfulness is measured based on the utility and relevance of the response, while harmlessness is evaluated throughout the entire response to reduce potential risks, biases, or harmful content. Three discussions in this section, we identify several areas where DeepSeek has made innovations and highlight potential future directions. Transformer architecture improvement. The transformer serves as the core building block of LLMs. While MLA improves the attention mechanism, MoE enhances the FFN block within the transformer. Together, these innovations have significantly contributed to the advancement of the DeepSeek v3 model. Advancements in transformer architecture can greatly influence both the effectiveness and efficiency of the training process. For example, a comprehensive ablation study of the decoupled rotary position embedding, as discussed in Section 2.1.3, could provide deeper insights. Additionally, further theoretical justification for the load balancing objective, as outlined in Section 2.2.3, would be valuable for future research. High sample efficiency. The introduction of multi-token prediction enhances the utilization of training data, thereby improving sample efficiency GIR plus 24. This demonstrates that better training efficiency can be achieved by developing algorithms that make more effective use of the training dataset. In Section 2.3, we mention the issue of the incurred longer training time, suggesting there is still room for further improvement. Co-design of algorithms, frameworks, and hardware. The dual pipe and FP8 mixed precision training are engineering techniques introduced to enhance training efficiency. These innovations emphasize the value of designing models from a holistic perspective, integrating architecture, algorithms, and hardware in the most effective and efficient manner. Recently, an improvement to the dual pipe has been made by QWHL25, as mentioned in Section 2.4.1. Reinforcement learning. The impressive performance of pure reinforcement learning in the post-training stage highlights a new research avenue in this area. The iterative training approach, which alternates between SFT and RL, is particularly inspiring. Furthermore, the introduction of GRPO demonstrates how a widely used RL algorithm can be improved to significantly reduce GPU memory usage. For conclusion, in this paper, we have reviewed the key innovative techniques that contributed to the success of DeepSeek models. These include innovations in the transformer architecture, techniques for improving sample efficiency, the co-design of algorithms, frameworks, and hardware, as well as the GRPO reinforcement learning algorithm and the application of reinforcement learning in the post-training stage. Our review highlights several open questions and potential research directions in this rapidly advancing field. References: Alch plus 23, Joshua Ainsley, James Leethorpe, Michiel de Jong, Yuri Zemlyansky, Federico Leber-On, and Sumit Sanghai. GQA, Training Generalized Multi-Query Transformer Models from Multi-Head Checkpoints. RZ